Okay, welcome back. So let's talk about what is the cause of these ice ages, right? So we've talked a little bit at this point about how we can interpret these ice ages to exist using oxygen isotopes, but what causes this pattern of ice ages over time? Because it is very cyclic in terms of its repetitive. So what we're going to do is a little bit of a review of orbital parameters. And we're going to start by talking about tilt and eccentricity. So once again, I'm going to go to the drawing board here so I can draw some stuff out. These may or may not be things that you've heard about before, but the first parameter is, actually, I'm going to go to black here. The first parameter is the tilt of the Earth, T-I-L-T. And so this is the idea that basically when the Earth rotates on its axis, right, it's rotating around on this axis, the axis is not straight up and down, right? Right now I'm holding my pen straight up and down. The Earth's axis actually tilts at about 23 degrees. It's a very, very minor tilt, so something like this, right, 23 degrees or so. And so it rotates around the axis on that tilt. So it is not rotating up and down, it is always tilted. So let me draw something like that. So here's the Earth, right? This dot, 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 dot. Oh, I'm going to have a hard time drawing straight dots here. Basically, that would be what's straight up and down. But the Earth, though, is tilted like this. So I'm exaggerating its tilt so you can see it a little bit better. But that is the tilt of the Earth. So if we say the sun is here, a happy sun, right? So if the sun is here, right, you can see that at this particular point in time, what we're looking at, the way I've drawn the Earth right now, the northern hemisphere is tilted towards the sun and the southern hemisphere is tilted away from the sun. Now, that is not always going to be the case, again, because as the Earth rotates around the sun once a year, right, it's going to come to a point where we're completely at the opposite of this, right? So again, here, this is the tilt of the Earth. If I'm the sun, right, let's say I start over here, right? So on this side, the northern hemisphere is tilted away from my face, but as we rotate around the sun in the other direction, the northern hemisphere is tilted towards my face. And so half a year later, 180 days later, it will look something like this, right? So here's the Earth, again with its tilt, highly exaggerated tilt in this particular case, still tilted in the same direction because the tilt is not changing. But in this case, the northern hemisphere of the Earth is tilted away from the sun and the southern hemisphere is tilted towards the sun. So here, the northern hemisphere, right, we'll say NH, northern hemisphere, has more light, and in this case, the southern hemisphere has more light from the sun. This happens, right, on June 21st, and this happens on December 21st. This is the summer solstice and the winter solstice. So this is the longest day for the northern hemisphere. This is the shortest day for the southern hemisphere, I mean for the northern hemisphere, the longest day for the southern hemisphere. And so this is what gives us seasons, basically. So tilt is the reason for the season. So we would not have seasons if it wasn't for the tilt of Earth. Okay, so tilt is very, very important. So the other property that we want to talk about is called eccentricity. I get my pen over here. Eccentricity. And so basically that is the shape of the Earth's orbit around the sun. So here's the sun in the middle. Happy sun. So the Earth's orbit is fairly circular, but it has a little bit of eccentricity to it, meaning that it can be a little oval shaped. Now I'm going to draw this very exaggerated so you can see what I mean when I say eccentricity. And so let's say that the Earth's orbit around the sun looks something like this. Again, I'm drawing very, very, very bad patterns here because I can't draw on this little thing. But let's imagine that the Earth's orbit around the sun is highly eccentric like this, which it is not. But it is slightly eccentric. It's like 0.2% or something. So it's a small number. But what this means, though, is that there are going to be times as the Earth travels around the sun that the Earth is closer to the sun than other times, right? So here's the Earth. At this particular time in its orbit, it's relatively close to the sun, as you can see here from the distance, right? If we, keep going all the way around the sun, rotating around, we're going to get to a point, the opposite end of the spectrum, where the Earth is going to be pretty far from the sun. And so when the Earth is closer to the sun, it is absorbing more sunlight from the sun. When the Earth is further away from the sun, it is absorbing less sunlight from the sun. And so those are going to be important, right? let's escape out of this and come back. And what we're going to do is talk about the fact that these two parameters in particular can reinforce each other. Oops, it's my calendar. Don't need to see that. There's nothing really on it though, but let's pull this back up. Okay, so we said tilt was the tilt of the Earth's axis, 23 degrees. And eccentricity is the shape of the Earth's orbit around the sun, which is a slight ellipse and not a circle. And so each one of those are going to cause variation in the sunlight. And as to say, eccentricity is a difference of about 6.6%, depending on whether or not it's closest to the sun or far away from the sun. Now, what is interesting about these parameters is that they can either reinforce each other or they can oppose each other. And so what I mean by that right now, for example, in the Northern Hemisphere, they oppose each other. And that's illustrated on this first figure here at the top, which unfortunately is not in colors. It's a little harder to read than I would like it to be. But the Northern Hemisphere is leaning towards the sun when it is furthest away from the sun. So it's getting more sun because it's tilted towards the sun, but at the same time, it's on the far end of its orbit, right? And so those two parameters are opposing each other in the Northern Hemisphere. The Southern Hemisphere, though, is the opposite. So in the Southern Hemisphere, it's leaning towards the sun when it is closest to the sun. So at that point on the orbit around the Earth, the Southern Hemisphere is closest to the sun, like I'm holding the pin close to my face. So it's closest to the sun at the point on its orbit when the orbit is also closest to the sun. And so what that means is that those two parameters are reinforcing each other in the Southern Hemisphere. And you can sort of see that by the way they've drawn this diagram here. The combined parameters are shown in the dark. And so it's this one that I have my mouse on right now. But it's like if you imagine these both as waves, if waves look the same, they're reinforcing each other. And so the light from the tilt and the light from the eccentricity are enforcing each other in that particular case. And so we end up with this bigger curve. So that's going to be important. Now, one of the things, though, that is interesting to us as scientists is the fact that this relationship, this reinforcing relationship that we see between tilt and between eccentricity can change over time. And so it doesn't necessarily always have to be the case that the Northern Hemisphere is the opposite and the Southern Hemisphere is reinforcing. And when I say reinforcing, I'm specifically talking about solar insolation, so the amount of sunlight that reaches the Earth. So it is more right now in the Southern Hemisphere and less in the Northern Hemisphere. But that has not always been the case because of the third parameter in the Milankovitch cycles, and this is something called precession. And precession is basically wobble. So if you've ever taken something like a spinning top and spun it, what you will see is that it wobbles around the top, right? So it makes this big circle. I'm kind of exaggerating what that looks like here, right? But it makes the big circle at the top as it spins around, right? That is its wobble. The Earth does the same thing. It has a very small wobble. It's not significant, but it is wobbling just a little bit, And so what that means then is that the Earth, right, because of this wobble, the wobble then is affecting the tilt and the eccentricity, right? Because at some points in time, it's going to be wobbling so that the wobble is a little more, that direction. Sometimes it's at on the point of its wobble when it's the other direction. And so that is changing the tilt. It's not changing the tilt so that the tilt is like this, right? The tilt is always in the same direction, but it's wobbling around that tilt. And so what that means is there can be minor changes in the tilt over time. Precision varies about every 21,000 years. Eccentricity, the whole cycle, is about 100,000 years, and tilt is about 41,000 years. And so if we look at all these together, and it's actually just to give you an idea of what the ranges are here. Tilt ranges from 22.5% to 24.5%, and eccentricity from 0.01 to 0.07. Like I said, they're very small numbers, so it's mostly circular. And right now we're at 0.02 or 3, maybe perhaps. But it is enough to have these variations. And so each of these different cycles, which again, each has its own specific range of time which that cycle varies over. So for example, when I say 100,000 years for eccentricity, what I mean is it takes 100,000 years for that eccentricity to change from the highest number, from 0.07, down to the lowest number, 0.01. And so every 100,000 years, we go from one end of that cycle to the other. With obliquity, which is tilt, it's 41,000 years. And so every 41,000 years, we go from the lowest tilt, which is 22.5, to the highest tilt, which is 24.5, right? So that's an entire cycle. If we look at all these cycles together, what we see is that they work together over time to change the amount of solar forcing, or the amount of insolation from the sun that is hitting the earth. And this is particularly prominent in the northern hemisphere. And it can actually change temperatures by as much as 25% at high latitudes, right? And so if you think about where glaciers are when we have periods of glaciations, that should make sense, right? Because glaciers tend to be in the northern hemisphere of the planet, because that's where we have the most significant change. So there's about 5 degrees total between glaciation periods and and periods of interglacial periods, right? So about 5 degrees difference between those different periods there. And let's see if we go to the next slide here. How do we know that these things are actually, what is controlling the ice ages? Well, if we look at this diagram here, this is a figure that is looking at the insolation over time, how total insolation has changed, and the rate of ice volume. There's an exact correlation between the amount of sunlight and the amount of ice on the surface of the earth. And so we then can go back to this previous diagram here, which is that solar insolation, that solar forcing, and know that it is the Milankovitch cycles that are controlling solar forcing in the long term, okay? Now, I will say though that there are a couple of things about the Milankovitch cycles and about glaciations that we don't understand. Right now, for example, if we think back to that very first figure we looked at when we looked at the oxygen isotopes, we noticed that those periods, right, the amount of time it takes to go from a glaciation to an interglacial period is about 100,000 years. And it's been like that for the last 500,000 years. But prior to that, or prior to at least a million years ago or so, what we see is that those glaciations were about 41,000 years in terms of the period. So the total period between glaciation to interglacial period was 41,000 years. And it was like that up to about 5 million years ago. So a million years ago, something changed, and eccentricity became the more important factor, the more important Milankovitch cycle, right? That is affecting the solar insolation, and thus affecting the timing of these glaciations. Before that, it was tilt. So tilt was more important in affecting the timing of these interglacial and glacial periods. We don't really know the answer to why it changed. We also don't understand why we didn't see, or why we don't see any evidence of glacial cycles prior to 5 million years ago. This seems to be a relatively new or recent thing in geologic history. It may have something to do with the positioning of the continents, right? As we moved out of more of a Pangea formation at the end of the Mesozoic into the Cenozoic, and everything started to separate and things moved around. We talked about the fact that where the continents are located is a very important thing. So it may have something to do with that. People are trying to work to solve that problem, but it is a very strange problem. But again, the important thing here is that it is the Milankovitch cycles, so the tilt, the eccentricity, and the precession, that are controlling these glaciations, these interglacial and glacial periods. So I'm going to stop there, and then we'll come back into the last part of the lecture, where we'll talk more about some short-term climate change.